Hello, physics students. Please excuse me for a moment because I forgot something in my storeroom. I'll be right back. Ah, there it is. How did I walk through that cement wall? You already know the answer. Magic. Just like when Harry Potter and Ron Weasley walked through a brick wall to get to platform 9 3/4 to catch the Hogwarts Express in Harry Potter and the Sorcerer's Stone. Great book. So you already are equipped to understand such things. Just like if while I was talking, I suddenly appeared in a new location. You wouldn't be shocked by that because it would be just like Draco Malfoy and the Vanishing Cabinet in Harry Potter and the Half-Blood Prince. But what if you were here in this room and you saw me walk through that wall with your very eyes, no special effects? What if while you were talking, or while I was talking, I was shifting around my position as you just saw? That would be the most amazing day of your entire life. In fact, you probably wouldn't forget that day for the rest of your days. But it would also be deeply disturbing. Imagine you're at home and you're talking to your parents and you suddenly wave over their shoulder and they turn around, nobody's there. And they say, "Who are you waving at?" And you say, "Oh, that's Roger." And they say, "But nobody's there." And you say, "Well, yeah, of course. That's because Roger popped in and then he popped out." Well, first your parents would think you're joking. And then if they asked you questions and realized that you were serious, they would be deeply disturbed. Probably the first thing they would do is take you to the hospital to check, get a bunch of blood work, make sure nothing's wrong, like severe dehydration can cause, I believe, hallucinations. They would check for maybe brain tumors, serious stuff. Maybe they'd give you a drug test to make sure you weren't on drugs. And if you passed all those things, then they might even, or probably would check you into a mental hospital so you could get treatment for some kind of mental condition. Because that's just not how reality works. We're so sure about reality working a certain way that if anyone observes anything different, and it's not special effects, but they observe it for real, we don't believe them. Even if it's their own child, they will not believe you because they believe their view of reality more, okay? So now you're in a position to understand what happened to physicists in the early 1900s when they started discovering that electrons could do the exact things that I just did. Electrons could go through barriers that, according to the old way of thinking, like your parents, like you, what we call the classical view, they should not have gone through those barriers, and yet somehow they went through almost magically. Electrons appearing out of nowhere in a spot where there was no electron. And this wasn't just one electron in an experiment, some obscure experiment. The more experiments they did, experiment after experiment, they started to discover that that is the true reality of all electrons. They exist in this almost magical way that completely shatters our understanding of what reality is. And so, what they had to do is reformulate all the theories of reality to match what the world was showing them was actually true. Now, when I first started learning about this, it's called quantum physics. It was, and to this day remains, the most fascinating thing I have learned in my entire life. And that's the topic for today. My only hope is that I could get you to also be as amazed as I was and continue to be with this quantum physics, this new version or the new reality that physicists discovered more than 100 years ago. Now, this amazement is not just me, okay? I want to read you a quote. Okay. This is from Niels Bohr. He won the Nobel Prize in 1922. So we're not talking about some out there person, metaphysical person. No, this is a hardcore physicist who made what you probably learned in chemistry, the Bohr model of the atom. Huge pillar in science, in physics. He said this: if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So if you're not profoundly shocked by the end of this video, it's because I did a bad job showing you the amazing new discoveries of what reality really is. And again, this is the reality of all particles on the subatomic level. What they do, going through things, popping in and out of existence, things that would blow your mind. And that is this right here. This is made of such particles: protons, neutrons, electrons. The air I breathe, the food I eat, my body, your body, were made of these fantastical things. That's the subject of today's video. But before I go into the theory, first I want to summarize that view that your parents hold, that I held, that you hold about reality. That basically, if you observe something different, the view is held so tightly that you're viewed as insane. That view, the old view, is called, in physics, we call it classical mechanics. So let me reconfigure the camera so I can summarize that view on the board. So your parents might say, well, those things couldn't happen because, for one, things are solid. Like, for example, I couldn't go through the wall because that would mean at some particular time, if I went through the wall without breaking a hole in it, at that moment, me and the wall would be two objects in the same exact place at one time. That can't be. You can only have one object in that spot. And then when I popped from one place to another, again, they might say something like, well, you can't do that. Things are where you put them, and then they have to be moved to a new location. They can't just go from one place to another. So said among physicists, we would say there's the classical view, which is that the world is made of solid particles that are interacting. According to Newton's second law here, now I wrote it out, A equals F net over M. We've been using this for a good half of the year. But we never really went into the philosophical implications of this equation because they're pretty profound. F net, what that is a statement of the present, a cataloging, like an accounting of the present. What's happening on me at this time? What are all the forces pushing on my body at this moment? On the other side, we have acceleration, which, if you think about it, really predicts the future. How so? Well, look at this basic equation if the acceleration is constant. Beginning at rest, d equals 1/2 at squared. I could find out where I am in 1 second, 2 seconds, 3 seconds by just plugging in my answer here into this formula, and I'd find the displacement moving in a smooth, continuous fashion from point A to point B, no discontinuities. Or if I wanted to, I could plug in distance and figure out what time it would take me to get there. So everything is nice and predicted. And what's in the middle is an equal sign, which in math is an absolute statement. It doesn't say acceleration is sometimes equal to F net over m, probably equal to F net over m, most of the time. No, it says equals all the time. And what that implies, the classical view, is that the future follows from the present. I missed a word. So you'll tuck it in your notes. From the present in a smooth and continuous fashion, which we label as sanity, okay? So, to show you the new way of thinking, there's a zillion experiments that show you in beautiful form, in provocative, interesting, profound ways, the new reality. But unfortunately, many of them you wouldn't understand because you haven't studied enough physics. But there is one I can think of that if we talk about it, you'll see where the new theory comes from some very strange behavior of an electron. So I'm going to move the camera to set up the experiment. This setup will allow me to simulate that experiment. Now, in the real experiment, the electron is electrically trapped in a given region. Essentially, I have a tiny particle trapped in a tiny box. Now, according to the classical view of physics, the electron is a solid particle, and when I throw it to a side with a certain speed and therefore a certain kinetic energy, as soon as I let it go, there are no more forces on that electron. So it'll go, according to Newton's first law, objects in motion stay in motion unless acted upon. It'll go at a constant velocity and therefore a constant kinetic energy until it gets to this point. At this point, there's a near infinite electric field that creates an enormous force on the electron, which essentially reverses the electron instantaneously with no loss of speed and therefore no loss of kinetic energy. Now the electron's going this way with a constant speed, constant kinetic energy until it gets to this point, bounces off this wall and goes back and forth, same speed the entire time. Now this setup, as I said, will allow me to simulate, but there's some problems with this setup. The electron goes at a constant speed, whereas this accelerates and decelerates with simple harmonic motion. But it's the best that I could do to create a back and forth motion repeating that will simulate that back and forth motion of the electron. What I want you to do, though, is focus on the bars. The car is too big, so the bars will be representing the electron. So first I'm going to move these aluminum bars like this to block almost the entire view of the car. So all you see are essentially the bars. Another problem with this setup is that there's friction. So when I release this, it will quickly lose amplitude. So what I'm going to do is I'm going to move it beyond the wall, the bars, and I'm going to release the car, and as friction gradually reduces the amplitude of oscillation, eventually I'll get to a cycle where it begins and ends at the walls of our box. So let's do that now. There, that was a good one. Now let's copy and paste that cycle over and over again to simulate the electron's continuous back and forth motion. But there are other modifications that we would have to make so that this setup is more like the electron in an electrical box. First, the electrons move very fast, so let's speed up the film a bit. Next, electrons don't make any noise as they move, so let's remove the sound. And finally, we can't see electrons, so let's remove the light. Basically, all we have left is a black screen, and that's because unless we get really clever, we have no idea where a single electron is. So suppose we invent ways to measure where the electron is at a given time. I won't go into the details, but physicists figured it out how. Essentially, think of it as taking a photograph of the electron. Now, if the electron behaved classically, then this is what the photos would look like. Notice that the electron is snapped in all places with equal frequency, which is what you would get if the electron was like a ball bouncing back and forth between two walls without any loss of energy. But that is not what happens. The next series of images show what the photos would actually look like. You should notice an interesting pattern. Notice that the images all cluster around the center of the box, but there isn't a single one of the electron at either wall. And that pattern would hold if you took 100 photos, 1,000, or 1 billion. And that's very strange, because how can the electron bounce off the wall if it never even reaches it? Next, suppose we wonder if this unusual pattern holds if the electron goes faster. Now suppose it currently has 1 electron volt, or eV, of kinetic energy, and we tried to add another 1 eV, we would find that it does not absorb that energy. Even if we hit it 1,000,000 times with 1 eV, it just would not speed up. So we tried 2 eV, same thing. But when we try 3 eVs, which would give the electron a total of 4 eVs, the original 1 plus the 3 extra, then this is what happens. Notice the pattern? You should see that now there are 2 regions where the electron gets regularly photographed, one to the left of the midpoint and one to the right. Again, it is never found at the walls, even if you watch for 1,000,000 years. And just as interesting, it is never found in the center of the box. How strange. More on that later. Now we try another 1 eV. We could hit it 1,000,000 times with another 1 eV and it just will not speed up. So we try 2, nothing. Well, 3 worked last time, so let's try adding 3 again. Nothing. 4, again nothing. But when we try adding 5 eVs, it absorbs it on the first try. Now it has 9 eVs of kinetic energy. It had 4 and we added 5. And then this pattern emerges. Notice that again, the electron is never found at the walls of the box. Again, even if you watch for 1,000,000 years. But now there are 3 regions where the electron is found. One in the middle of the box and 1 region on either side of the middle. And in addition, there are 2 other regions where the electron is never found. The spaces between the regions it appears in. Now you may not realize it, but all of these peculiar observations suggest a certain kind of behavior. We actually did an experiment investigating it earlier in the year. Do you remember? Let me give you a hint. The first harmonic looks like this, right? If I shake faster, the second harmonic looks like this. If I shake faster still, the third harmonic looks like this. Each time I have looks like this. Each time I have more and more antinodes. I could make the 4. That's right. The electron, what we thought of as a solid particle, is actually exhibiting wave behavior. Now, the first person who wrote an equation that said particles were actually waves was a man named Louis de Broglie. He wrote this equation back in, I think, 1924, and for writing this and stating that concept, he won the Nobel Prize in 1929. So very quickly, people realized the importance of thinking about a particle as actually a traveling wave. Now, the expression says that the wavelength of any particle is Planck's constant, which we know, it's on our reference table, divided by the momentum of the particle. Now, if the particle isn't moving too fast, we could use the classical expression for momentum, mass times velocity, kilograms times meters per second. So let me create a pause to allow you to copy these notes down. Now, there's a problem here. We know the wavelength, but what's the amplitude, what's the frequency, what's the velocity of the wave? So there's a lot missing. Well, it was about a year later that another physicist named Erwin Schrodinger wrote an equation that allowed us to determine these things. So are you ready for that equation? We'll find out. Here it is. That's what we call Schrodinger's equation. Don't panic, okay? So there's a lot here that you have no idea about. So first of all, this h with a bar over it, it's kind of like related to Planck's constant. We don't need to get too much into it. This triangle is actually a 3-dimensional derivative. So you need calculus, college level calculus, to understand what this is saying. This is also a derivative with respect to time. This Greek letter, phi, is the wave function. So Schrodinger didn't tell us what the wave function is. He gave us an equation that allows us to figure out, to solve for the wave function of a particle in a given situation where there's a particular kind of voltage that varies throughout the space. Obviously, this is heavy stuff. But if you could solve for the wave function of a particle in a given region, then basically what you have is all of this information. And here's where things get interesting, because the particles themselves do not exist as particles. They actually exist as the wave functions. So you solve this for wave function. That Greek letter. And then it's the wave function that exists in space. So like an electron's not moving as a particle, it's moving as this wave function. So that's the first point. So they don't exist as particles. There's no ball that's an electron. It exists as this wave. And then that wave function moves through the universe and interacts with the universe and other particle wave functions. Even more interesting though, these wave functions are not things you can see. You can't even touch them because they're not real. Let me write some statement down. The wave function is actually complex. You might be saying, yeah, that looks complex to me. No, I don't mean complex like in the everyday term. I mean in the mathematical sense, which means that complex things are not real. Okay, so complex, not real. The electron is not real. It's literally imaginary. And again, I don't mean like imaginary like unicorns. I mean in the actual mathematical sense. Look at this I here. This is a term you can recognize from math. I is the square root of -1. It is literally an imaginary number. And that's what an electron is. Literally imaginary, moving through space. That's not me saying that. You could see it right in the equation. And also, I want to share with you a quote by Werner Heisenberg. He won the Nobel Prize in Physics in 1932. Again, I'm not talking about someone, with crystals like a psychic or something. This is a heavy hitter. This is one of the great physicists of all time, certainly of the 20th century. You know Heisenberg from chemistry. You've probably heard that name. This is what he said, quote, "The atoms or elementary particles themselves are not real." His own words. So there's a lot to digest here. But what I want to do is go back to that experiment I modeled with the car moving back and forth, the electron in an infinite square well. Let's rethink it with the new theory, and then we'll try and extract as much information about how the universe actually works for these fundamental subatomic particles. So I'm going to actually switch to the paper view because I found it more convenient than the chalkboard. So let's go to the paper view. Now this experiment is officially called the infinite square well. As I said, it's like an electron stuck in a box. Now the classical view of this situation is that the electron is a particle bouncing back and forth between these two walls. Now, a fancy way to say that the particle can be anywhere with equal probability is with this graph. This graph says that the probability of finding the electron near the wall here is the same as the probability of finding it in the middle or near the other wall. The probability distribution is even. The electron can be found anywhere according to the classic view of physics. Also note that the electron can have any kinetic energy that you give it as it bounces between these walls. But that is not correct. An electron is not a particle, not a solid thing. It's actually an imaginary wave. And just like when we studied waves on a spring, when you trap a quantum wave in a region, then you get standing waves. That's the only possibility. And the simplest case is the first harmonic, where we have just one antinode in the middle and two nodes at the end. Now remember what I just wrote on the board. The significance of this Schrodinger wave is that the amplitude squared tells us the probability of finding a particle like the electron in a given region. So notice here the wave has 0 amplitude, so when we square 0, we get 0. In other words, there's no chance of ever finding the electron at the wall. Same for this wall. But if you square this, you get a peak here, meaning the electron's most likely to be found in the middle, but it can basically be found anywhere in this region. Note also that we can find the wavelength of the electron's wave using de Broglie's expression and the kinetic energy from just 1/2 mv squared. Now, as I keep trying to add energy, the electron will not accept that energy unless I give it enough to get it to the second harmonic. And that is the case when we have 2 antinodes and 3 nodes in the wave trapped in the box. Again, amplitude squared tells us the probability of finding an electron in a given region. The amplitude here is 0, 0, 0. When you square 0, you get 0 squared. So the probability of finding the electron at the walls, 0. It will never, ever touch the walls of the box. Interestingly, too, it will never, ever be in the middle of the box. Now, more on that later. Now, if you look at the de Broglie expression, you see that in order to get a shorter wavelength, which is what we have, right, shorter wavelength in the second harmonic, you need a higher speed. In fact, with half the wavelength, you need twice the speed, which means 4 times as much kinetic energy. Remember during the demonstration, I said 1 eV, the electron could only jump to 4 EVs, not 3. Okay, so this wave nature explains that peculiar behavior of the electron. The next situation is that I can add more and more energy, and it will only absorb the energy if it could go to the next harmonic, the third harmonic. Now, in the case of the third harmonic, we have 3 antinodes and 1, 2, 3, 4 nodes. Again, the significance of the amplitude of the Schrodinger wave function is that when you square it, you get the probability of finding the particle in that region. 0, 0, 0, 0 amplitude. Squared is 0, 0, 0, 0. That means, again, the electron will never, ever get to the walls of the box. And now it has 2 places where it will never be. Even though it's bouncing back and forth, they will never be here, never be here. And there are 3 regions where it could be found. Now, if you compare that to the first harmonic, you could see that now we have 1/3 of the wavelength that we had before. So with 1/3 of the wavelength, we have 3 times the velocity or speed. And therefore, when you triple the speed, you get 9 times the kinetic energy. So again, this is now, because we are looking at the electron as a wave, we can now understand why that energy comes in those fixed jumps. So let me create a pause to give you a chance to copy all these notes down. Now, let's talk about the implications of all of this. The first, we've already seen that the kinetic energy of the electron can only be changed by fixed amounts. And the fancy word for when something can be changed only by fixed amounts is quantized. This happens so often in the theory that, in fact, the entire theory is named after that behavior, quantum mechanics. The second implication, for almost all times, the electron exists as an imaginary entity. And I don't mean imaginary in the sense of, like storybooks. I mean it in a mathematical sense. Most of the time, the electron is this wave function, which includes I, which is the square root of -1. And related concept then, the electron as a particle can be nowhere at all. Another implication, the electron is in multiple places at the same time. Doesn't make sense for a particle, but as a wave, you could see this wave exists all throughout the box. So it is in multiple places at the same time. Another implication, the electron can be multiple waves at the same time. Remember, when we studied standing waves in class, standing waves are actually two waves moving past each other at the same time. One moving to the right, one moving to the left. When they interfere with constructive and destructive interference, that creates the illusion of no side-to-side motion, only up and down motion. Another implication. This is a fascinating one. At least I find it very fascinating. Let's take this harmonic right here. Notice that the electron, if you might photograph it, it might be in this region because there's an amplitude squared here that's non-zero. Say at a later time you photograph it over here. That means the electron was here, and then it was here. It went from A to C without ever going through B, and it's stuck on a one-dimensional track. Absolutely fascinating. This brings me to a quote. I read a lot of quotes of Nobel Prize winners. Well, I decided to get into the fun myself. I wrote this a couple years ago. Ghosts really do exist. They are called electrons, protons, and neutrons. If you think of the electron as not a solid particle, but like a ghost in a bad horror movie, going in and out of walls, appearing in front of you, disappearing, you have a better grasp of what the electron is than if you thought of it in the old, sane, rational way as a particle zipping around and flying and crashing into things. Again, the insane view, if you believed horror movies were real, people wouldn't really respect you much, but yet that's how subatomic particles actually exist most of the time. You're closer to the reality by believing it to be a ghost. Well, I had a little fun. Let's move on. This one is very fascinating. So I've been saying we snap a picture of the electron. You might be saying, wait a minute, I thought you said that the electron is a wave that you cannot see, you cannot touch, you cannot feel because it's imaginary. But this is a really interesting, mind-blowing thing of the theory. The way the electron can and does appear as a solid particle. When? When a person looks. The wave function disappears and leaves behind a particle. Fascinating, because we think of the world, the universe, as existing independent of us. Again, people would think you're crazy if you said, well, I turned around so the coffee cup doesn't exist anymore because it's behind my back. And yet, in quantum physics, this comes up over and over again. An observer, simply by looking, and I put that in quotes because you can't see the electron, but by doing an experiment where you try and find the electron, so human decides, they put a detector there, the wave function will disappear and the electron as a particle will appear. Now, before I answer the question where, I want to, again, share a few quotes, again, because this may sound unbelievable to you, so I want to list some quotes of some real heavy hitters of the 20th century. Here's a man named Pascal Jordan. He knew Einstein. They were, contemporaries. So it's not, again, someone out there. But he said this: observations not only disturb what is to be measured, they produce it. What a crazy idea. You observe a coffee cup and you produce the coffee cup. All right, not on the level of the coffee cup, but it is that way with electrons, protons, and neutrons. This is such a crazy idea, such a new idea that is so far removed from the classical, or I said the sane view of reality. Not everyone could accept it. In fact, Albert Einstein was a big critic of quantum physics. He could not accept quantum physics to his dying day. History proved Albert Einstein wrong. We could forgive him. He had so many great theories. But Albert Einstein, trying to object to this idea, said the following: I cannot accept quantum mechanics because I like to think the moon is there even if I am not looking at it. So Again, does the moon disappear when I turn my back? Does it reappear when I turn? Well, that's kind of like what the theory's saying. All right, that's too complicated an example. Albert Einstein is simplifying, but that's essentially, with electrons, protons, and neutrons, the reality that was facing the scientists. Now, one more quote before I move on. This one, I mean, this really blows my mind. I say that over and over in this video. But here's one by Martin Rees, who's a physicist who is still alive, I believe. So here it is. In the beginning, there were only probabilities. The universe could only come into existence if someone observed it. It does not matter that the observers turned up several billion years later. The universe exists because we are aware of it. So think of what that quote is saying. The universe did not exist several billion years ago. Several billion years later, we came into existence. We observed it now. So now it existed several billion years ago. This is getting to another fascinating thing about quantum mechanics, that some people see in the theory the possibility of changing the past, okay? Mind-blowing stuff. Again, you have to buy books to really get into it. I'm not going to get into it anymore because, again, this video is long enough. Let's move on. The final point. So where does the particle appear when I look? The wave function disappears. The particle appears. Where? Well, I already mentioned this. The probability of a particle appearing somewhere is proportional to the amplitude squared of the wave function. The determinism of the Newtonian world was shattered. Why? When I look and the wave function goes away, the electron could appear here or here or here, anywhere this amplitude squared is not zero. But you may be saying, well, there's got to be a way to know. Well, according to every experiment, there is no way to know. The electron's appearance is at a truly random position somewhere within this region. Now, remember Newton's laws. I hit a baseball with a bat, it's going to land somewhere. It's going to fly through the air according to a certain path. Quantum physics says no. It can jump around into existence anywhere where there's a wave. It could pop out of the wave imaginary form and become a particle at some random location. Again, this caused Albert Einstein a lot of problems. Here's another quote by Albert Einstein. God does not play dice with the universe. He could not accept this. And why? Well, Albert Einstein believed in God. He had a certain view of how God made the universe. By the way, a lot of physicists are or do believe in God. A lot don't. It's just, again, one of those things that looking at the universe could lead you down either path. It doesn't say, oh, it's all rational, there's a God, there's no God. No, you could believe either way and still be a great physicist like Albert Einstein. Unfortunately, in the case of Albert Einstein, his conception of God in a certain way forced him to fail to grasp quantum mechanics and to be too prejudiced with his thinking. But it really is according to this principle that Schrodinger mentioned. Now, the last thing I want to do, talking about this experiment, is finish up the quote that I started by Werner Heisenberg. Again, heavy hitter, won the Nobel Prize in Physics in 1932. He said this: the atoms or elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of things or facts. So that's a beautiful way to state the true nature, the full implications of this incredible theory, quantum physics, especially as it pertains to the infinite square well. So, is your mind blown? I know when I first learned about this stuff, mine was, okay? So just incredibly fascinating. And I just want to emphasize yet again that this is not just some stuff that was happening in obscure experiments 100 years ago. This is probing the nature of all subatomic particles. Every electron is doing this, every proton, every neutron. So when you look at this, that insane world of things going in and out of existence, being in multiple places at once, going through things, two things being in the same place at the same time, responding to humans, all that stuff is really happening here. It's happening, as I said, in the air you breathe, the food you eat, in your own body. Fascinating stuff, okay? Now, another point. You might be thinking, well, if this is happening, how come I don't see it? Why can't I really walk through a wall if that's really the reality that's happening? Okay? Why don't I see people going in and out of existence, popping from one place to another? And the reason why, in order to explain that, I typically give students the following analogy. So imagine, here you are today. Tomorrow you find out you win the lottery. Maybe all the lotteries in the world. You're a billionaire. You're the richest person on earth. Suddenly, right? What does that mean? Well, you don't need to go to college. You could buy your own house. You could buy houses all over the world. You could buy a private jet. You could fly, be in, I don't know, Australia in however long it takes the plane to get there, a few hours. That is incredible, unimaginable freedom, going anywhere on earth. But think about that from the perspective of some being living in a solar system on the far end of the universe. And they're looking in their telescope, and they see a little tiny flashing light that's our sun. And then the being next to him says, hey, I'll tell you something interesting. Next to that flashing dot, there's a little speck you can't even see. It's called planet Earth. And on that planet is a person that can go anywhere they want. They can fly, live anywhere, buy houses, North Pole, South Pole, wherever they want. And the being's squinting in the telescope and they say, go anywhere you want? He's on that little dot over there. He can't go anywhere. So the reason why we can't see this stuff happening is a matter of scale. It is the reality of everything that makes us up. But when we look at atoms and the electrons are going all over the place in all this crazy manner, we just see it as a speck. We can't even see the speck, right? So the concepts we have, that things stay put, that they move smoothly from one place to another, it's true on our scale of living. But it's an illusion. It's not true. It's not the true nature of matter. Another fascinating thing, how come we can't feel? How come for so long we developed these ideas about reality that were false? And so if we can't see it, you might be saying, well, who cares? And that's fine. You could say that and just, do the homework, whatever, go on. But there are people who do care because they find things like that interesting. You're looking at the night sky, and what if you look, just a bunch of specks of light. What if someone told you that on every speck of light, there's the dynamic world of people living there? Well, then you don't really understand the night sky, do you, if you just think they're twinkling lights? So, yes, it is knowing the truth that is interesting, fascinating, blows your mind. So also, I could give you some other examples. You might still say, I'm still not interested. Well, think about this. Have you ever thought, is there fate? Is there destiny? People ask these questions, right? So they wonder, I met this person. It was meant to be. It was fate. We came together. Well, quantum physics says something about fate. Think about an example. I hear this sometimes. People get cancer and they survive and they say, it was meant to be because it taught me how to live. So it was fate. Well, think about what quantum physics is saying. When that photon comes in, as I talked about in a photon unit, and hits your DNA, it creates an influence, a voltage on the wave function and alters it. But what happens? Does that electron shift into a position that causes a cancerous DNA, or does it stay put? The photon changes the odds. So maybe you had a 1 in a trillion chance of having cancer. Now all of a sudden that photon hits and it's 1 in 5 or 50-50. But what actually happens is completely chance. The amplitude squared, oh, I don't have it written down. Where the electron actually ends up is proportional to the amplitude squared of the wave function, but there's no causality. It's just strict chance. So even whether you actually got cancer or not, according to quantum physics, completely just a random fluctuation. Interesting, right? So thinking about fate. This is why Albert Einstein again said God does not play dice with the universe, because he couldn't accept that. There had to be fate, there had to be things. So that is the final thing I would say. I want to say a couple more things. If you are interested in these things, then there's a lot of books you could buy and read. Look online, look them up. People, oh, why would I buy a physics book? People do. Like, for example, you've heard of Stephen Hawking. Here's a book of his, A Brief History of Time. Famous book. People who never study physics, maybe they studied poetry or something, and they buy these books because it says things about fate in the universe that blow people's mind, fascinate them. So if you're interested, read reviews on books and pick up, Stephen Hawking again. This is a great physicist, right? We're not talking about people just shooting out ideas. These are some of the smartest people who lived, and they're telling us this beautiful, interesting knowledge. Well, that's it for today. Again, I hope you were deeply fascinated like I was. I hope it causes you to think about your things, your life, the universe, and possibly read and study more. So I hope you enjoyed that, and I hope you enjoyed the video. I'll see you in the next physics video.